Let us now turn our attention to some of the limitations and considerations of DeLauney's that is most critical for you to understand. In previous videos, we demonstrated that when DeLauney's triangulation is applied to points, each point is evaluated with respect to every other point in the xy or two-dimensional plane. Even though these points are joined to form three-dimensional triangles, the determination of an acceptable triangle is based on the 2D circumcircle of each triangle and subsequent points. What this means is that any two points with the same xy position but a different z or elevation value will not process correctly. Put simply, DeLauney's triangulation does not support perfectly vertical faces or overhang geometry. For survey data, this means that the surveyor will intentionally slope the face of a vertical surface so it will show up in your existing ground. This horizontal offset may only be a tenth or 100th of a foot, but the points will have some xy or horizontal difference for a vertical face to be represented in a terrain. This limitation also has important ramifications for how you should approach your template design and road modeling. Being able to accurately represent tops, bottoms, or intermediate layers of your design can be important for surface-to-surface quantity analysis. Further, downstream engineers, surveyors, and contractors using your model data will require that your project be delivered in a form and format that will produce accurate DeLauney's compliant surfaces in the applications they use. There are too many applications in our industry to fully list here, but nearly all of them require delivered surface information to be DeLauney's compliant, meaning the data from one software, like OpenRoads, can be imported and retriangulated in some other application without errors. Now let us look at an example of a dataset that contains points that have been collected which have the same horizontal position but unique elevations to see how this affects the final triangulation. Here we have a set of points. These points represent a floor and a wall. As you can see, the wall is perfectly vertical with respect to the floor, and we have points that are aligned to match this vertical face. When you have a data set like this, the final triangulation will never result in an accurate representation of your surface, and inaccurate results will most likely be inconsistent between various applications. Let us consider some possible results you may see from triangulating these points. Here, in the first window, the points at the base of the wall are ignored and only the highest values are incorporated into the terrain. In the second instance, we see that the lower values are retained and the top of the wall points are excluded. While these are both possible results, probably the most common output looks something like this third case. Here you have a random combination of higher and lower points that result in a jagged surface. When reviewing your models and associated terrains, a jagged output like this is a red flag that you have a combination of points and break lines with two or more elevations for the same XY position, which is incompatible with DeLauney's triangulation.